Welcome to my channel or the Big Structural Hub. This is a place where you learn, build, and innovate. Today, I want to solve this problem on the board. It is a question from a past paper. That is question number 5, October, November 2014, Higher Diploma, Kenya National Examination Council. The question reads, figure below shows the plan and a section through a timber floor for a building. Design the timber joist of strength class C16 given the following information. Joists are spaced at 400 mm center to center. Joists have an effective span of 3.5 meters. Self-weight of T and the G board is equal to 0.1 kilonewton per meter square. Self-weight of ceiling is equal to 0.2 kilonewton per meter square. Imposed loading on floor is equal to 1.5 kilonewton per meter square. Depth of joist is limited to 200 millimeter. Density of timber 540 kilogram per meter cubic. Then K8 1.1, K3 1.0. Depth factor K7 is equal to 300 over H raised to power 0.11. Maximum depth to breadth ratio as given in table 2. Assume any other relevant information. So this is the plan. As you can see, this is the floor plan. It has joist. These are the joist. 1, 2, 3. Spaced at 400 millimeter center to center. Again, it has a 200 by 380 timber binder. It has a bearing. This is the bearing distance from here to here, 100. Again, an effective span of 3,500 center to center. So, and this is the section. If you can cut through section XX, this is what you will have. So we have T and the G floor decking, and then timber joist, then plaster board ceiling. So let's see how we can solve such a question. Solution. Let's begin. Solution. So the first thing to do is to determine the section size of the timber, considering that you have been told the depth joist is limited to 200 millimeter. Then another useful information is the maximum to breadth ratio is given in table 2. So I will proceed to table 2 and show you the maximum to breadth ratio. So that is the table. As you can see, number 1, no lateral support. The maximum depth to breadth ratio is 2. And number 2 is end held in position. So the maximum depth to breadth ratio is 3. And then end held in position and the member held in line by purlins or tie rod at center not more than 30 times breadth of the member. So as you can see on our plan, you can use plan to determine the condition of the joist. So for ours, we have, for our case, we will use the maximum depth to breadth ratio as 4, because the end, it says that end held in position and member held in line by purlins or tie rod. As you can see, our joist is held in position at the end. Then at the center is held by a timber binder, or it can be a purlins. So the depth, the maximum depth to breadth ratio will be 4. As you can see, where my cursor is 4. So the depth to breadth ratio is equal to 4. But we have been told the depth is 200 millimeter. So it means 200 to B is equal to 4. So we can get B by making B the subject of the formula. So if we take 200 over B is equal to 4 over 1, it implies B is equal to 200 over 4. Therefore, B is equal to, so B is equal to 50 millimeter. So our section size is 50 by 200 millimeter. After getting our section size, we will proceed to calculate the total loading on the joist. So I will wrap this section because we have already utilized this information and this information. So I will wrap to create more space for more calculation. So for us to calculate the total loading, we will need to calculate the self weight of the joist because we have not been given the self weight of the joist. What we have is the self weight of T and the G board, which is 0.1. Again, self weight of ceiling, 0.2. And then in post loading on floor, 1.5. So if we take the self weight of the timber joist plus the self weight of T and the G board plus the self weight of ceiling, it will give us the dead load. So self weight of joist. So this will be area times the density of timber. So the area is 50 over 1,000. We are converting from millimeter to meters times 200 over 1,000 times the density of timber. Density of timber is 540. That is 540 kilogram per meter cubic. We will convert from kilogram to Newton per meter cubic by multiplying 540 with gravitation acceleration, which is 9.81. By doing so, we will have converted from kilogram to Newton. And then we multiply by 10 raised power negative 3. That is from Newton to kilo Newton. So the answer is 0.05. 0.05 kilonewton per meter. After calculating the self weight of joist, we'll come here and add other weights. So we have the self weight of both, which is 0.1, which is 0.1 plus 0.2 plus 1.5. All are in kilonewton per meter square. So the answer will be, so the answer is 1.8. 1.8 kilonewton per meter square. As you can see, our weight is in kilonewton per meter square. So we reduce from kilonewton per meter square to kilonewton per meter. So reduce to kilonewton per meter. So you will take 1.8 kilonewton per meter square times the spacing of joist, which is 400 millimeter center to center. So times 400 over 1,000. We are converting from millimeter to meter. So that one will be 1.8 times 400 over 1,000. So that is 0.72 kilonewton per meter. Now, total loading is equal to load of the joist, weight of the joist, which is 0.05 plus 0.72. This is kilonewton per meter. So you will get 0.77 kilonewton per meter. So if you can draw our beam, our joist here, so that is 0.77 kilonewton per meter, and then the effective length is 3.5. So M max, maximum moment will be W L square over 8. So the W is 0.77 times L, 3.5 square over 8. So our answer will be the answer is 1.18 kilonewton meter. Again, you can calculate your reaction. Or the shear force, which is V. This one will be WL over 2. So our W is 0.77 times L, 3.5 over 2. So our answer will be 0.77 times 3.5 over 2, 1.35 kilonewton. So this is our V. After that, you can proceed to modification factors. So modification factor, so we'll begin by K3. K3 is 1.0, as you have been told in the question. Again, K8 1.1. Then K7 is equal to 300 over H raised to power 0.11. So this one will be 300, H is 200 over 0.11. So which imply K7 is equal to 300 over 200 raised to power 0.11. So the answer is 1.05. That is K7. After modification factor, we'll proceed to grade stresses. And we will use class 16 to obtain grade stresses. Class 16. So you have stress in bending parallel to grain. And then we have stress in compression perpendicular to grain. Again, we have stress in shear parallel to grain. Let's proceed to our tables. So that is the table. You can see class 16. That is class 16. So bending parallel to grain is 5.3. 5.3. Newton per millimeter square. And then stress in compression perpendicular to grain, stress in compression 1.7. So we will use the minimum value 1.7. So that is 1.7. 1.7 Newton per millimeter square. And then shear parallel to grain. Shear parallel to grain. That is 0.67. 0.67 Newton per millimeter square. Then E mean. The E mean will be our E mean as you can see is 8800 Newton per millimeter square. So 8800 Newton per millimeter square. What follows next is the permissible stresses. So the permissible stresses, permissible stresses. So we have stress bending parallel to grain will be, this is the admin, will be K3 times K7 times K8 times stress in bending parallel to grain. So this one will be K3 is 1.0 times K7 1.05 times K8 1.1 times 5.3 Newton per millimeter square. So the answer will be The answer is 6.12. 6.12 Newton per millimeter square. We proceed to permissible stress in compression perpendicular to grain. So this one will be K3 times K8 times stress in compression perpendicular to grain. So K3 is 1.0, K8 1.1 times 1.7. So K7, it modifies the bending only. K3, it modifies all the stresses, and also K8. The answer is 1.87 Newton per millimeter square. We proceed to the last one. This one will be K3 times K8 times stress in shear parallel to grain. So 1.0 times 1.1 times 0.67. The answer is 0.74. 0.74 Newton per millimeter square. From here, we proceed to design consideration, and we will begin by bending. So again, I will rub here to create more space for calculation. So we begin by bending. Now, design consideration will begin by bending. And the formula for bending is Z is equal to M over F. Our M is 1.18 kilonewton meter. So we multiply by 10 raised power 6 to change from kilonewton meter to Newton millimeter. So we'll have 1.18 times 10 raised power 6. And our F is the permissible stress in bending, which is 6.12 Newton per millimeter square. Therefore, Z is equal to 1.18 times 10 raised power 6 over 6.12, which imply Z is equal to 192.81 times 10 raised power 3 millimeter to power 3. And then this is the Z required. We proceed to Z provided. Z required 192.81 times 10 raised power 3. Then Z provided will be BD square over 6. So our B was 50. and our D was 200 square over 6. Then you punch your calculator to get your answer. So the answer is 333.33 times 10 raised power 3 millimeter cubed. Therefore, the section is okay in bending because Z required is less than Z provided. Therefore, section okay in bending. We proceed to shear. Shear. So Q shear is equal to 1.5 V over BD. So this one will be 1.5 times V. Our V is times V 1.35 times 10 raised power 3. We are converting from kilonewton because our V is in kilonewton. So we multiply by 10 raised power 3 to change from kilonewton to newton. Then times B. Our B is 50 and our D is 200. So our answer will be 0.20 Newton per millimeter square. So you will compare this with the permissible stress in shear parallel to grain. So if we compare 0.20 will be less than 0.74 Newton per millimeter square. Therefore, section okay in shear. From there, we proceed to bearing. We check the bearing. We proceed to bearing. So Q bearing is equal to V over Bx. Our V is our shear force for our reaction. Our B is the breadth and X is the bearing distance. So our V is 1.35 times 10 raised to power 3. We are converting from kilonewton to newton. And then our bearing distance from our diagram is 100. No, we begin with B. B is 50. And then times our bearing distance is 100. Like that. Again, you punch your calculator to get the answer. So the answer is 0.27. 0.27 Newton per millimeter square. You compare with the permissible stress in compression perpendicular to grain. So our permissible was 1.87. So it means 0.27 is less than 1.87 Newton per millimeter square. Therefore, okay. in bearing. We proceed to the final design consideration, which is deflection. So our final design consideration is deflection. The permissible deflection is given by 0.03 times span. So it will be 0.03 times the span is 3500. It gives you 10.5 millimeter. Then you come to induced deflection. This is the formula for induced deflection. Our W is 0.77 kilonewton per meter. We convert from kilonewton per meter to Newton per millimeter. So the the value will remain the same, but the unit will change from kilonewton per meter to Newton per millimeter. The reason is 1,000 Newton is equal to 1 kilonewton. Again, 1 meter is equal to 1,000 millimeters. So it cancels out. We have the length of 3.5. If we convert, you will get 3,500 millimeter. Our E is 8,800 Newton per millimeter square. Our I is BD cubed over 12. So you will get 33.33 times 10 raised per 6. Our area is length times width, 50 times 200. That is the value. So you insert this value into the formula. Then you punch your calculator. You will get your answer as 5.39 millimeter. So this is our induced deflection. So for our joist to be okay in deflection, the induced deflection should be less than the permissible deflection. As you can see, 5.39 millimeter is less than 10.5 millimeter. Therefore, section okay in deflection. And that marks the end of that question. We meet again in my next session. And those who have not subscribed, please subscribe and hit the notification bell so that you may be the first person to be updated when a video is uploaded. So thank you for your time.